All right, guys. So here we go. We got question number 3 on the 2026 AP Chemistry exam. So again, another 10-point question. If we look at the prompts, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 prompts. So that means each one is worth 1 point. So let's see. Yep, 10 prompts, 1 point. Okay. So the first question, they give us a Ka reaction, so it's showing the acid acting like a base with water, or sorry, an acid with water, right? You're getting hydronium, and it's the Arrhenius definition of an acid, but it's also the Bronsted-Lowry definition. They're asking for a conjugate acid-base pair, just one of the pairs from this reaction. So you have two choices to choose from here. You could do the nitric acid and nitrate or nitrite, and then or you could do the water and hydronium. But you had to clearly label which one is which. So in this conjugate pair, HNO2 is the acid and NO2 minus is the base. But in this pair, the water is the base and H3O plus is the acid. Okay, so you either had this or you had that as your conjugate pairs. Okay. All right. So if we go back here, so it gives us a solution of nitric acid. It tells us the molarity and the pH. So remember, we have the pH, we can calculate the H plus concentration. We don't have to do a Ka shortcut. This is a low Ka value, but maybe not low enough to do the 5% rule. And we don't have to use the 5% rule. You would use the 5% rule if you're thinking you're using your Ka shortcut. But we don't have to solve for X using the 5% rule. We can solve for X by doing 10 to the negative pH, right? So be careful of using the 5% rule here. We're not going to do it. Okay, so let's go to that. So what did I say here? Okay, so we can still think of the Ka shortcut, but it would be the Ka shortcut without the 5% rule for for B number 2. Okay, but all we have to do for this first thing is just remember H plus and hydronium are synonymous. So H3O plus equals 10 to the negative pH, right? So 10 raised to the negative 2.09 will be our molarity of hydronium, or our molarity of H plus. It's the same thing, right? So we'll do 10 to the negative 2.09, and that comes out to be 0.0081 or 8.1 times 10 to the negative 3. And again, remember your reporting units of molarity, so capital M or moles per liter, right? So our hydronium concentration in that acid solution described in part B is that, right? That's our hydronium concentration. Now, it would also be the concentration of nitrite, right? The NO2 minus concentration, right? Because for every 1 hydronium, you're going to get 1 nitrite. If you go back and we look at the reaction, right, for every 1 of these produced, you're getting 1 of those. So the molarity of this in the solution of hydronium is going to be equal to the molarity of nitrite in the solution. Okay. And then for part 2, it's saying calculate the concentration of this at equilibrium. So remember, this is the initial concentration. And, if we're doing quick calculations and do I have the Ka shortcut written out, right? So remember, we can use the shortcut and just assume that the concentration of nitrous acid is at equilibrium is essentially what it started with, because not much disassociates because it has a low Ka value. But we already figured out what X is in the shortcut. Remember, X in the shortcut represents the hydronium concentration. We already figured that out. So without the 5% rule, we're just going to take the initial concentration of the nitrous acid, and subtract the molarity of H3O plus, which we calculated before, because that's what X represents. And that's what the true concentration of this is going to be at equilibrium, right? So we take the starting amount, subtract the amount that we lost, which is equal to the amount of hydronium that we have, right? Because it's a 1-to-1 ratio, and we get our new molarity. Now, I probably should say 0.12, right? Because, this, but remember, it's subtraction and it's really about decimal places. And so this was 0.00 810. So like, I think this is, this is fine. Okay. But that would be the answer for the nitrous acid concentration. Okay. We keep going. They do another experiment, or they do an experiment. So you have the same concentration of acid, but you're at a higher temperature, right? And notice what happened. The concentrations of nitric acid or nitrous acid went down. And remember, the nitrite and the hydronium in the previous one at the previous temperature was 8.1 times 10 to the negative 3. And now it's, 1.2 essentially times 10 to the negative 2. So the amount of product increased and the amount of reactant decreased at this higher temperature, at the new equilibrium position of the reaction. So that means an increase in temperature favored the forward reaction. Okay. And so it's saying first, just calculate the new Ka. So we can go and calculate the new Ka. And so it would just be the concentration of hydronium and nitrite squared divided by the equilibrium concentration of the HNO2 that they gave you. And then you get that Ka value. Okay. Now, for number 3, you didn't have to say it this way, but I think that they described it. They described it, justify by answering, comparing the Ka values. So, right, we have to compare the Ka values, right? So what was the original K value? Something times 10 to the negative 4. And this new K value is also, what was it? Sorry. Times 10 to the negative 3. So the equilibrium constant increased as temperature increased, right? That's a sign of an endothermic reaction because heat favored the products, right? So I probably not going to get my point here because I didn't pay attention and I didn't compare the Ka values. And that's the easiest one to do. But I was just saying that it clearly showed that an increase in temperature favored the products. And so if you add heat and it shifts the reaction towards the products in terms of Le Chatelier's principle, that means heat's a reactant, and that means you have an endothermic process. Okay. If K goes up as temperature goes up, equilibrium constant, it's an endothermic process. Okay. All right. So now we did a titration with the same acid. Okay. We didn't know what the concentration was in this, but they did a titration with this molarity of NaOH. They started with 35 milliliters of the acid in their flask. They slowly added the sodium hydroxide to it until it was completely neutralized, until we got to the equivalence point. Okay. They give us the equation of the reaction that's happening, but all we need to know is this would be the equivalence point, right? So just like different things we could get just from looking at the chart that they gave us. Right here I have, so sorry, let's go back to the first one. Like, remember, if K increases as temperature increases, endothermic. If K decreases as temperature increases, exothermic, right? Okay. All right, so back to this, right? We got our equivalence point, and that's at 50 milliliters of NaOH added. So if we're doing our titration calculation, that would be the volume of the base, right? If we divide that by 2 and go to 25, this would be called the half equivalence point. If they ask, we know the pH at this point is equal to the pKa of the acid, right? The negative log of the Ka, right? We know this volume at 12.5 would be the volume of the half equivalence point, okay? So all that kind of good stuff just by looking at the titration curve, all right? So part D was just say what the pH is at the equivalence point. So you got to know which point is the equivalence point. If we go to the chart, the point of inflection, and it's 8, right? So pH of 8. All right. And then part E is just figuring out what the molarity of the acid was from the titration data. So again, so remember, it's monoprotic acid. The base only has 1 hydroxide. So we could do like a stoichiometric calculation, or we could just do molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. Remember, the molarity of the base was given to us here. So that's where that number comes from. The volume of the base was found on the chart, 50. The 35 milliliters of the acid is what we started with, and we're just solving for that, right? So when we solve for it, we get the molarity of the acid solution was 0.23 molar, okay? And then this one, it's kind of like understanding that, you know, this region of your graph is the buffer region, but the midpoint of the buffer region is when pH equals pKa. But what does that really mean in terms of the Henderson-Hasselbalch? It means at the half equivalence point, moles of this, or moles of that equal moles of that in the flask at that time, okay? And what you need to know is anything before that point, so anything along here, you have more of the acid than you do its conjugate base. And then anything beyond this, you have more of the conjugate base than you do of the acid. And then at the equivalence point, you don't have any more of this. You don't have any more of that. They've all taken each other out. And what do you have? You have this weak base in solution only. And that's why the pH is above 7 at the equivalence point, because now you have a weak base in your flask, right? Okay. But we needed to know that about the buffer region, and they're asking when is the concentration of the HA, you know, higher than A minus. So if you just drew an X anywhere in this region here, right? Anything between 0 and 25 degrees Celsius, or not 25 degrees Celsius, 25 milliliters added, anywhere along there before 25 would be a perfectly good answer. So what did I put? I put, so yeah, I just described it. So again, on your test, whoops, on your test, you would, you know, maybe put an X here, you know, okay. But anywhere before 25 milliliters added would be fine, okay. And then if we go to the next one, we got a little Hess's law. I call it Hess's law, but you know, we got to get these two equations to add up to this one, and then we got to know what to do with the equilibrium constants to get the new equilibrium constant. We could probably just quickly realize that we're going to have to reverse this reaction and keep this one as is. Remember, if you reverse a reaction, you take 1 over the original. So since this is in scientific notation, the new K, when we reverse this reaction, will be 1 times 10 to the positive 14 instead of negative 14. And this K value will keep as is. And then when these two add up to this one, all we do is multiply these two K values to get the new K value, and that's our answer. So the new K value is going to be the original Ka value from the chart, and then 1 over the Kw value that they gave you, because you had to reverse that reaction to get them to add up to the equation that K2 describes. So it's just going to be the Ka times 1 over the Kw, and that'll give us our new equilibrium constant. All right. And then the last one, right? The student is saying that for this titration, they think methyl orange is the right indicator. And we should immediately disagree with that student, because that changes color at around a pH of 4, but we needed our indicator to change at a pH of 8. Right? So understand, like if you used the methyl orange, you would get a color change at around this point, where maybe you've added 45 milliliters of the base. And because of the color change, you're going to think you've hit the end point of your titration. So instead of using 50 milliliters of the base, you're going to say it only took 45 milliliters of the base. That's going to undercalculate the number of moles of HNO2 that you have in the flask. And so it would underestimate the actual molarity of HNO2, because you thought it took 45 milliliters when it really took 50 milliliters to reach the equivalence point, right? So you want your indicator to change color at a pH that's as close to the equivalence point as possible. So we want the indicator to change color around 8, not down here around 4, right? And we wouldn't want to use this indicator, because that's not going to change in time, right? That's not going to change until I'm at a pH of a little bit more than 12, right? So the thymol blue would be the best indicator, and so we disagree with the student, right? Right. So disagree, this would show the equivalence close to 45 milliliters added and would undercalculate the molarity of the HNO3, right? Bad choice, okay? And that is question 3. So that covers question 3 on this year's AP exam. We'll come back for the next video and we'll start the shorter questions, questions 4, 5, 6, and 7. All right. Have a great one.